In this video, we take a look at an integration technique known as trigonometric substitution, or trig sub. Okay? This is useful for all sorts of different situations where we have an integral that none of our other techniques work for, and I'll try to outline that as we go. To do that, I want to look at an example here. Find the area of the circle with a radius of 1. Well, we already know what this area is just with our basic geometry definitions, right? We know the area of a circle is pi r squared. So plug in 1, we get pi. Of course, area of our circle with radius 1 is pi. I want to verify that with some integration, okay? And we couldn't have done this kind of up to this point without what we call trig sub. So if I write down the equation for the unit circle, x squared plus y squared is 1, and I solve that for y, I get square root 1 minus x squared. Now, technically, I need a plus or minus there. That would give me both the top and bottom half of my circle. So what we're going to do here is we're just going to work with the top half. It's a little bit easier to integrate. That way, it's just, we can use symmetry to our advantage. So the top half of my unit circle is just given by that square root function there. And to find the area under that curve, I'm just going to integrate from minus 1 to 1 of that function, right? Square root of 1 minus x squared, all with respect to x. But this is an integral that we can't do with the techniques we already know. We know that this should be pi over 2, right? Because the area of the unit circle we know to be pi, divide it in half, we get pi over 2. None of the techniques I know can help me integrate this really right now. I would try to substitute or rewrite. Even with integration by parts, this doesn't get me anywhere that's really nice with this integral here. You could try to set up a couple different things and work your way around it, but really this is kind of set up nicely for what we call trig sub. And what we should note is that square root of 1 minus x squared kind of looks like square root of something squared minus something squared, right? I've left open parentheses there. And what we're going to learn in this video will kind of translate to almost any situation where we have that format, right? Square root of something squared minus something squared. And what we know about trig is basically all founded upon the Pythagorean theorem, right? And for us, that's going to come in the form of something like a sine squared plus cosine squared is 1. And when I manipulate that and I solve for sine squared or cosine squared, I see things like 1 minus sine squared or 1 minus cosine squared. Right? We're used to these a little bit from the previous section, working with these trig integrals. And actually, most of the integrals in this new section here will kind of result in some of those old trig integrals. But just about every integral that this technique will be useful for is something like, 1 minus sine squared, 1 minus cosine squared, or similar. Okay, there's some other techniques we'll explore too. So I want to evaluate this integral, square root of 1 minus x squared. I've dropped the bounds. I'll handle those in a little bit. And what I want to notice is that is this guy 1 minus sine squared of x. Okay? Well, what that means is I have to actually change variables. So right now I'm working with x's. This would be then a change of variables to thetas. Okay, so I'm basically then making a substitution. And if what I've written there is any sort of correct or can be made correct, then x would have to be sine of theta. Okay? There's kind of a technique to help us work our way around this and figure out where does this 1 minus sine squared come from? How do I know that that's what I want to use? And again, it all comes from our Pythagorean theorem. Sine squared plus cosine squared is 1. We know from, pre-calculus or trig that we have sides of a right triangle on our unit circle where the opposite side of my angle theta is sine of theta, the adjacent side is cosine of theta, and the hypotenuse is always going to be 1 on that unit circle. So this would work for a circle with any radius, right? But our example is dealing with the unit circle, so that's why that hypotenuse is left as 1 there. So what I want to try to do is replace everything in my integral with something in terms of theta. And hopefully that takes it to something that I can actually then integrate. Yes, there's going to be trig, right? There's going to be trig functions involved, but hopefully we can handle that. We have some guidelines to help us. So you might remember Pythagorean theorem more so as like x squared plus y squared equals z squared, or a squared plus b squared equals c squared is what I often write. So the sides of my triangle then I can quickly replace with just a and b, right? So to satisfy my Pythagorean theorem, a squared plus b squared should be equal to 1 here. So c is 1. And what I notice about 1 minus x squared is it's kind of like I've solved for one of the sides. Right, I see 1 minus x squared. That looks a lot like a squared equals c squared minus b squared, right? There's that minus in between, and that's going to be something we want to pay attention to. Where's the minus sign in our radical? Is there one at all? And then how does that affect the shape of the substitution I'm going to make? So I see a 1 minus x squared. I see something like c squared minus b squared. So for us in this case, for this specific integral, my c is going to be like my hypotenuse, and that's going to have a value of 1, as it does already, and the b or a, these are kind of just labels, right? The important one is the hypotenuse. The other two sides, it doesn't really matter. I could say that this is b squared equals c squared minus a squared. So I've got some freedom there. But that other side, one of the other sides is going to be then x, okay? So I can go ahead and replace here my a, b, and c's with the parts that I have in my radical, okay? So my a then is like the square root of 1 minus x squared, right? I actually have a side of my triangle, or my proposed triangle, in my integral, okay? So this a is going to be my square root of 1 minus x squared. The b is going to be x, that's the leftover side. How do I know that this is any sort, that this makes any sort of sense? The Pythagorean theorem needs to be satisfied. So if I were to square both of the opposite and adjacent sides, add them together, they should equal the hypotenuse squared. So when I square the square root of 1 minus x squared, I'm going to get 1 minus x squared plus x squared should indeed be equal to 1. Those x squareds are going to cancel, and I've got a truth statement, right? I've got something that's true. So I know that this triangle makes sense with the setup that I have, with the radical that's in my integral, and how I've written the sides of my triangle. Now again, we solved kind of for a here. We could have solved for b, right? So what that means is that the hypotenuse with the minus sign is really the only thing that matters. So that 1 absolutely has to be on the hypotenuse. You can try to rearrange the sides in a couple different ways, and you'll see that this way is one of the ways that satisfies the Pythagorean theorem. The other way is if I were to switch x and the radical. If I switch those, this would still satisfy the Pythagorean theorem. So I do have some choices. What now? So I've got what I would call the setup to be able to do a substitution in my integral for theta. Okay, so I'm going to trade x's for thetas, and it's not a one-to-one trade. If I look at my triangle here, I want to write down what x is as it pertains to theta, right? So which trig function would I use to write down x by itself? Well, I see that x is going to be related to sine of theta, because sine is opposite over hypotenuse. How do we remember that? I do by SOHCAHTOA, right? Sine is opposite over hypotenuse, x over 1. Okay? So sine of theta is just x, or x equals sine theta. I need that bit, because if I'm going to replace everything in my integral with my theta variable, that means I need to replace dx as well. This dx has to be something in terms of d theta. So we write down x equals sine theta so we can take a derivative, dx, and get something to replace dx with. Cosine theta d theta. Derivative of sine of theta is cosine of theta, and I need a little bit of chain rule there. Gives me my d theta. Okay. So that dx cosine theta is going to replace the dx in my integral, and I'm going to replace all the x's in my integral with a sine of theta. So what I've got is 1 minus x squared would be like sine squared. Dx would be like cosine d theta. I can wiggle some things around here. What we're going to want to do is try to simplify this down, break it down as much as we can. And the reason these work out nicely is because of the Pythagorean theorem, because I have this nice formula for sine squared and cosine squared. 1 minus sine squared there I can write as cosine squared. That under the radical simplifies rather nicely. There's still this cosine of theta d theta outside. Of course, square root of cosine squared is just a cosine. Oh, I've actually written that wrong. Oh, no, I'm sorry. It's right. Square root of cosine squared is cosine times the extra cosine on the outside. I should have a cosine squared left over. It just looked weird. So my integral is all left with a cosine squared. Along the way, this doesn't really seem like it's going to be all that helpful, but cosine squared is something that we integrated through the last section. Okay. I'm going to go to the next slide here in just a second. I can find a form for that integral. When cosine was even, we used a power reducing identity. So we said cosine squared was 1/2 1 plus cosine of 2 theta. And that's something I can integrate rather easily. 1/2 theta plus 1/2 sine of 2 theta, right? So antiderivative of cosine of 2 theta is 1/2 sine of 2 theta. I'm going to use this to then find the area of my semicircle, right? So I'm putting all of this back into the context of my circle problem. There's the area that I'm looking for. Again, that's half the area, basically. And that I can write then as the integral 1/2 integral 1 plus cosine of 2 theta. So I already have that integrated. I know what that is. But I've gone a step back here because I have bounds. I have bounds of integration. Okay. Originally, they start where x is minus 1 and x is 1. But I've switched now to thetas. So my bounds should also switch to bounds in theta. If x is equal to sine theta, then I want to know what theta is when sine of theta is 1. And that's just a kind of a simple calculation backwards. It's what angle makes sine equal to 1, and that's pi over 2. I have to be a little bit careful here because of the domain of the inverse sine function, but I then need, when x is minus 1, sine of theta, what angle makes sine of theta minus 1, and that's going to be a minus pi over 2. And that's just a little tricky, but it's because of the domain of inverse sine that I use those two guys. So my bounds of integration now in theta are minus pi over 2 to pi over 2. So I integrate that 1 plus cosine of 2 theta to get the 1/2 theta plus 1/2 sine of 2 theta, and then evaluate from minus pi over 2 to pi over 2. Plug those in, and it's just number crunching from here. When I plug in pi over 2, for theta, I get pi over 2 plus 1/2 sine of pi over 2 times 2 would give me a pi. Minus what I get when I plug in a minus pi over 2. In for theta is a minus pi over 2 plus 1/2 sine of a minus pi. I'm just missing a parenthesis there. Oh, I actually don't need that. This all breaks down because sine of pi and minus pi are indeed 0. Okay? So when all is said and done here, I end up with pi over 2 minus a negative pi over 2 is plus pi over 2. Pi over 2 and pi over 2 is pi. All divided by 2 is a pi over 2. That should be the area of the semicircle, right? The upper half of the unit circle, and that makes some sense, right? That's what we found the area to be. So the area of my circle is going to be 2 times this integral area, 2 times a, 2 times the area of my upper half of the circle. So that's 2 times pi over 2, or pi. Of course, area is pi r squared. So I use this example, something that we already know and we can verify easily, so that the calculus and the integration makes sense, right? It's not a coincidence that we get pi here. We know we should. Yeah. So we're going to explore in a couple other examples here. This above technique is what we call trig sub. Okay, I'm doing a substitution with trig functions. And it's a little tricky. It'll take a little bit to get the hang of. But the stronger your trig is, I think the easier that you'll find this. So you might want to go back and review a little bit of your right triangle trig and figure out the relationships between theta and the sides of a right triangle. Let's do an example. I've got the integral of dx divided by x squared times the square root of 9 minus x squared. So for just about all of these integrals, there's going to be some sort of radical a squared minus b squared, or a squared, something under the radical that has two squared terms and either added or subtracted together. So that we got to be a little careful. We can easily break where we would want to use trig sub. If that was a minus 9, then trig sub might not work the way we want it to. But so far here I see a radical, and what I want to try to do is relate that to my Pythagorean theorem, right? So I'm looking at that radical, and kind of right away I'm already thinking trig sub. I'm thinking that I can make that radical one side of my triangle, use the other parts in my radical, the 9 and the x squared, as parts of the other sides of my triangle, and make a substitution. And so I see that this radical here is kind of like solving for a side of the triangle, right? It's very similar to that first example we did. This looks like a squared plus b squared equals c squared solved for a or b, right? So, I know that because I see 9 minus something else, 9 minus x squared. So the one side of my triangle is going to be the radical, right? That would be like a or b. The other two sides, my c is again the important one. The hypotenuse is the one that matters most. Because that 9 is kind of listed first and I'm subtracting away from it, we always subtract away from the largest side of the triangle. So what I see here then is that c should be 3, or c squared is 9, so c should be 3. And again, that comes right from solving the Pythagorean theorem for one of the sides, a or b. So when I solve for like a squared there, I see c squared minus b squared. So that c squared should look like 9, right? That I'm always just kind of trying to match those up, figure out where that subtraction is, and then my hypotenuse should be nearby. So I've got a 3 on the hypotenuse. The other two sides will be either the radical or x, okay? And it doesn't matter which goes where, but typically one side, the radical, I'm going to put that on the adjacent side, and then the x goes on the other side. Okay? Again, this triangle should satisfy the Pythagorean theorem. If I were to square that radical, I would get 9 minus x squared, add the opposite side of the angle, x squared to it, I would end up with 9 equals the hypotenuse squared, 3 squared. 9 equals 9. Yes, Pythagorean theorem is satisfied just with a quick check. So I need to then replace everything in my integral with thetas, okay? So the first thing we do is figure out how to write down a relationship between theta and x, okay? So for us, I look at my triangle and I see that I can get x paired with 3 if I use sine. Sine of theta is opposite over hypotenuse, x over 3. I then always write down what x equals by itself, multiply both sides by 3, x is equal to 3 sine theta. I do this so that I can take a derivative of x and get dx, because dx needs to be replaced in my integral as well. So I've got dx is 3 cosine theta d theta. So all that's really left is the radical, okay? So what I like to do is I have x, I could plug what x is in for all the x's in my integral. That totally works. But since I have my triangle here, I can work a little more, if I'm comfortable with my trig, to find what the radical is with respect to theta. So I know that I can write the radical paired with the hypotenuse, right? 3 and the radical with respect to theta using cosine. So what I'm going to do is rewrite the radical as cosine of theta. Cosine of theta is the adjacent over the hypotenuse, the radical 9 minus x squared over 3. Solve that for the radical so that I have something to plug in for that entire radical expression. You'll see what I mean. So I've got all the parts that I need to make my substitution. So what I've got is an integral. The dx on top is replaced by the dx down below here, 3 cosine theta d theta. Okay. I replace x squared by what x is squared. X is 3 sine theta, so I'm going to square it. Right? 3 sine theta quantity squared. The radical then is replaced by 3 cosine theta from my triangle, 3 cosine theta. Okay. That's probably the hardest part of this, figuring out which sides of the triangle correspond to what parts of my integral, and then writing everything in terms of theta. Okay. It takes a little bit to get used to. So I can now cancel. I see that 3 cosine theta and 3 cosine theta disappear. I'm left with d theta divided by 9 sine squared. Okay, so this is a trig integral, and hopefully it's easier. I don't have to do too much with the techniques we learned in the last section. Sometimes these boil down nicely. I'm going to pull this 9 out as a 1/9, and 1 over sine squared is cosecant squared. That's something that I know the antiderivative of. It's kind of a happenstance that we ended up with something that's kind of one of our basic formulas. It's one that we don't use too often, but indeed, what derivative do I take to get to cosecant squared? Well, that's a cotangent. In fact, it's a minus cotangent. So the antiderivative of cosecant squared theta is a minus cotangent theta. Cool. We're done. We typically here, what happens is if we start with an integral with x's, we like to go back to an antiderivative that involves x's, right? I've got thetas with that cotangent. So all I really do is look back at my triangle and I figure out what cotangent is involving x. Tangent is opposite over adjacent, so cotangent is adjacent over opposite. Looking back at my triangle here, adjacent is the radical divided by the opposite is x. So what I've got is negative 1/9 times square root of 9 minus x squared over x, and of course plus my constant of integration. So there's just another different type of a trig sub, and in fact it's really similar to the last one we did, right? There was a 1 minus x squared in the last problem. This one had 9 minus x squared. So the shape was really the same. The sides of my triangle were basically the same or in the same format. Let's look at something a little different here where maybe that might change. I've got the integral of dx over 4x squared plus 1 to the 3 halves. I don't have an explicit radical here, but we have to remember that 3 halves, that power, is fractional. And when I have a fractional power, that really does indeed mean that I've got a radical in there. So what I can rewrite this as is dx over the square root of 4x squared plus 1, all then cubed. Right, so if this was all to the 1/2 power, it would just be the square root. But because it's raised to the 3 halves, it's the square root then cubed. Not a big deal. I just might have a little bit more work to do later, but really, I still have a radical, and under it, I see kind of what would be like a squared and b squared, or c maybe squared. So I then look to set up my triangle. I see that under my radical is a 4x squared plus 1, okay? Normally, or in the last 2 examples, I wouldn't say normally, in the last 2 examples, we had 1 minus x squared, or 9 minus. There was subtraction in my radical. And if you remember, I always subtract away from the longest side. I'm not subtracting here. So what that kind of indicates is that what I have under my radical is the sum of the 2 smaller sides. I've got kind of the hypotenuse already. 4x squared plus 1, it looks like a squared plus b squared. Yeah? And that's all just c squared. So what I can argue then is that c is the square root, that radical. It's the square root of 4x squared plus 1. I have the hypotenuse. It's just staring at me. 4x squared plus 1 under the radical. My two other sides then are a and b, 1 and a 2x. Yeah? It doesn't matter which side you put them on. Typically, we would put them like this. The opposite side would be a 2x, and the adjacent side would be a 1. And I'll show you why. Again, it doesn't matter. You can switch those sides, and everything would still work out. Your work and actually your answer might be slightly different than your neighbor or your friend, but it would still work. So the reason we put the 2x on the opposite side is when I go to relate x and theta, we can use tangent to relate the opposite and adjacent sides. So what I would get is tangent of theta is 2x over 1. If I were to have the sides switched, where 1 was on the opposite side, tangent of theta would be 1 over 2x, which is not the same thing. In fact, I would really have to use then cotangent of theta to make things, simplify nicer. So that's the reason we put that 2x on the opposite side, is so that we can use tangent. We don't have to think about the reciprocal trig function. That's cotangent. So I solve this for x. X is 1/2 tangent theta. And again, I always do that so I can find dx. Derivative of 1/2 tangent theta is 1/2 secant squared theta d theta. Not so bad. Hopefully, we'll see when we plug things back into the integral. And again, I always try to replace my radical. Okay, so what I want to do is relate theta and the radical, but not with 2x. If there's a 2x in my integral, I would relate it to 2x, but there's not. So I'm going to relate the radical and 1. So I can relate adjacent and hypotenuse with cosine, but that would put the 1 in the numerator. I don't really want the 1 in the numerator. I just want the radical, so I would use secant theta. So I can replace the radical then by just secant theta. So I'm ready to substitute. I've got everything I need. I replace the dx by 1/2 secant theta d theta. Secant squared, I'm sorry. I then replace the radical by secant theta. But I have to remember that that's all still cubed in the bottom. Oop, way too fast. That's all still cubed in the denominator. Okay? I see then that I've got powers of secant both in the numerator and denominator. And in fact, I can cancel 2 secant squareds from the numerator and 2 from the denominator, leaving me with just a d theta on top. The 1/2 I bring to the outside, it's a constant, and divide by secant theta. There's only a secant theta left over in the denominator. This boiled down very nicely. I thought that 4x squared was going to be troublesome because all I've had is x squared so far, but really it just came out as a constant. Not too bad to handle in terms of the integration. How do I integrate d theta over secant theta? Well, 1 over secant theta, I'm gonna bring up as cosine. 1/2 cosine theta is what I've left to integrate. That's an easy one. Antiderivative of cosine is sine. So then I have to go back, look at my triangle, and figure out what sine is in terms of theta. Sine is opposite over hypotenuse, so that's a 2x divided by the radical 4x squared plus 1. Just another little simplification here. I see that the 2's are going to cancel, and I'm left with just x divided by the radical. Very nice. Very nice. So once you get the hang of kind of how to set up your triangle, I always let the triangle kind of guide me, okay? I try to figure out, based on what radical I have in my integral, how does that pertain to one of the sides of a triangle, and then make the rest of the triangle around it and start to substitute. Start to write down the trig functions that are going to help me substitute into my integral. You're going to land somewhere with an integral from before. Maybe it's a basic one, like this example, integral of cosine theta. Sometimes it might be something more involved, right? We've already integrated cosine squared, and that was one where required a little bit more technique to it. Let's do another example. I want to showcase kind of one more type of these. So I've got the integral of square root of x squared minus 1, all divided by x dx. Okay, so square root, I'm going right to a triangle here. It's just x that's squared there, so I don't have any other constants really to worry about. And I notice subtraction now under my radical, right? I see x squared minus 1. That's got the shape of c squared minus a squared. It's like I'm solving for one of the other sides, right? It's like I'm solving for b or a. So what that indicates to me is that the x squared and c squared are going to match up. C squared is x squared, so then I can say the hypotenuse should be x. It's listed first with the subtraction. I'm always subtracting away from the longest side, the hypotenuse. Okay? The other two sides don't really matter. It doesn't matter which sides the next two pieces are on, I should say, whether it's opposite or adjacent. The radical always goes on one of the sides, and for me, that's going to be the opposite side. And the 1, then, the A or the B is going to be on the adjacent side. So I try not to specify exactly what A and B are, because that gets me thinking that I always have to do it that way. If you like that, that's okay. But I focus on the hypotenuse, and then the other sides I can move around to kind of whatever suits me. So what I've got here then is a secant theta substitution. Secant theta would be x over 1, right? We relate adjacent and hypotenuse with cosine or secant. And secant is the one that puts the x in the numerator. So that's what I want. X is equal to secant theta. So that means dx is equal to secant theta tangent theta. So the same process basically, right? Once I set up my triangle, this is a slightly different setup than before. I've got the variable listed first in the subtraction, and that tends to lead to a secant substitution, okay? So what I've got here then is secant theta is x, dx is secant theta tangent theta, and I'm pretty much ready to go. I usually like to put the radical in with one of the trig functions. So for me here, I relate then the opposite and adjacent sides. In fact, I can use just tangent theta is equal to that radical, right? Tangent of my angle there is the square root divided by the adjacent side is 1, so I just don't even really have to write the 1. And I can replace the radical with tangent, okay? I'm ready to substitute. In my integral here, the radical in the numerator is all tangent theta. Dx I can replace with secant theta tangent theta. In the denominator, I just have an x. No big deal. X is secant theta. And I'm good to go. Everything in my integral has been replaced with something involving theta. Don't forget about your dx. That's one of the biggest things that we tend to miss when we're making our substitution. I can cancel a little bit here. Secant thetas go away. And I'm left with two tangents, gives me a tangent squared theta d theta. So I've landed at a trig integral, something from section 8.3, that I can work with, and it's not too bad. I don't know any basic forms that give me a tangent squared, but I know some identities that involve tangent squared, and that's just secant squared is equal to 1 plus tangent squared. So what I can do is replace tangent squared by a secant squared minus 1, secant squared theta minus 1. When I integrate, this is nice because integral of secant squared is tangent, right? I've got a tangent minus the integral of theta is minus the integral of 1 with respect to theta is theta. So I've got a tangent of theta minus theta plus a constant, okay? Almost done. I just have to replace my thetas now with x's. I go back to my triangle and I try to figure out what tangent theta would be. Tangent theta is already written for me, right? I've written it. It's circled down at the bottom of my slide there. Tangent theta is the radical. I then have to subtract what theta would be. What on earth is theta? Well, I've got some options here. I know that x is equal to secant theta. And I know that tangent theta is equal to square root of x squared minus 1. I need to solve something for theta. I need a theta equals. So I can use either of those two expressions, those two equations, secant theta is x or tangent theta is square root of x squared minus 1, and solve for theta. I'm just going to pick one. If I solve tangent of theta equals square root of x squared minus 1, for theta, I get inverse tangent of the square root there. Inverse tangent of square root of x squared minus 1 plus a constant. Okay? So I had some choices there. I just needed to find some relationship with theta. I needed to find a theta equals, and there's a couple ways that I can do that. But this should work. This should work for me. Okay? What I want to do is kind of outline, I want to summarize everything that we've talked about here. And in fact, I can basically group these trig subs into 3 different types. The first type is if I've got integrals with a squared minus u squared. What we did, those first 2 examples, I made a substitution like u equals a sine theta, okay? I did this basically just by trying to set up a triangle. So for me, that triangle was u on one of the smaller sides, and a squared is listed first in my subtraction, so a should be the hypotenuse. If I want to make the substitution that's kind of suggested here as sine theta, then the opposite side should contain a u. Okay? These are really just kind of guidelines. They're not hard, fast rules. But that means the adjacent side is square root of a squared minus u squared. Okay? If you make that substitution in the case where you have a squared minus u squared, things usually work nicely. You're working with sines and cosines. The only thing that's really going to change is if I were to move my radical and my u, my adjacent and opposite sides. Okay, your integral is going to look a little different. If you do that, your substitution would be a cosine theta, but it's still absolutely useful. This is just the way that pretty much the textbook sets it up. This form, a squared minus u squared, we use a sine theta. The next type would be integrals with a squared plus u squared. And for those, we're going to make a substitution like u equals a tangent theta. Okay? So what my sides would look like here, I've got a squared plus u squared. That's going to show up in the hypotenuse under a radical. So my hypotenuse is going to be square root of a squared plus u squared. I've got substitution. I don't have subtraction. So that's the longest side. It's the sum of the other sides squared under the radical. Then the opposite and adjacent sides are u and a. It doesn't matter which one goes where. If I want to indeed make this tangent substitution, then u has to be on the opposite side, right? Tangent of theta would be u over a. If your u and a were switched, you would use a cotangent substitution. We don't like working with cotangents as much as we do tangents, so that's why we set up the triangle this way. And last but not least, the last kind of example we did, we had an integral with u squared minus a squared, x squared minus 1. Here we're subtracting away from the largest side. U should be my hypotenuse. And this situation, we're going to either make a secant or cosecant substitution, depending on the other 2 sides. We prefer secants, or at least I do, so I let a be the adjacent side, so that secant of theta is u over a. It's hypotenuse over adjacent. That means the radical has to be the opposite side, and we can then make our substitution. So most of the trig subintegrals you do will be in one of these 3 forms, right? So you can use these as guidelines. You can use these to help make your decision as to what substitution you'll make and then how the triangle is set up. I always try to let the radical influence the creation of the triangle and then use my triangle and my 6 basic trig functions of that angle to substitute into my integral. Practice a lot of these. They're very tricky, and just take some practice. Thanks for watching.